So, and our next speaker is Mooly Sagiv from Tel Aviv University, and is also founder and CEO of Certora. Yeah. So Mooly is actually an enigma in programming languages, work who I've known for many years, and he's published an amazing number of papers, highly influential papers, and has, just like as a promised Grigori, I will not mention all the honors. So welcome, Mooly, give us your talk on security again, or on static analysis. Thank you.
Yeah, so my talk is really connected to Gregorian's talk. I encourage you actually, if you can, just ask me questions during the talk. Sometimes I tend to talk too fast. I'm kind of too excited about this work. So this is actually academic work, but actually we have, in November, started the company. So our aim here is technology for formal verification, but actually, and that's the focus of this talk, even though I will talk a little bit about technology, it's about specification, as Grigori says, sort of how do you specify and what you specify. And some of it is actually acknowledged to the work that we got from collaborators and actually customers. So who are we? So actually, this is started by academic, our colleague Noam Rinetsky, now James Wilcox from the University of Washington, the folks at Stanford that helps us, and really the people who do all this work is Shelley Grossman, who's actually a PhD student who convinced me to do this company, and Marcelo Taube. They are the ones who did all of this work. And also I acknowledge the VMware help by Itai Abraham and Guy Gwet. So the pain point, I'm sure it's clear in this space, that software and Buggy software is everywhere. It's not just blockchain. And open source and the fact that software is changed is just making things worse. And code, we know that code correctness means safety, means many things. In the context of blockchain, it's even worse because the code is immutable. So once it's uploaded in the blockchain, it's really hard to fix it. And also, as Fritz pointed out, when you have money involved, it's really tricky. So what are we doing? The business case here is very clear. We actually have been in this space very small, but we are seeing a lot of traction. And I should acknowledge, I'm sure you see from looking at me, that I've been around for a long time. But the idea is formal verification. This is sort of the killer app of formal verification in many ways, because the bugs are really tricky. And if they are there, and once you have bug in financial transaction, it's really hard to undo this transaction. As a result, the customers are really willing to pay a lot of money, and I can give you, but they are willing to pay a lot of money. And what we do for them, we develop these techniques that make this verification a push button. So you write your contract in Solidity, in any language that you write, and then we check automatically that it's correct. And either produce a proof, but sometimes more useful, we provide actually an input that shows the bug. And that's very useful. We can actually take a contract and we are finding rare errors in this case. And as Gregorio pointed out, the biggest problem in this space is actually writing the specification. But the interesting thing in this domain, and it is hard in any domain, but these are financial transactions and usually are written by small code. And the idea is the customer, and that's at least what we see from our current customer, they are willing to do most of the work. So they are willing to help us in writing the specification. And in fact, in the process of writing the specification, they are finding bugs which has nothing to do with the code. So they are willing, it is a time-consuming effort. And I have been working in this space, for example, with the avionics software, and it's a different experience. This is an experience that people are really willing to. So in fact, our technology is very fast. We make it hard for them to actually, they write this spec, and it's difficult, and we help them. And it's very expensive, and they know we're very expensive. But the idea is that eventually they will not need us so much, and we are already seeing it. Another thing which is interesting, as Gregorio pointed out, there are standards. And even with ERC tokens, so the standard that you see in the ERC token is usually a very, very ill-specified. But we come with a very firm standard that has a lot of requirement. And then we check that. And the idea, this specification you can do once for many contracts. So what do we actually do? So what we do, we have basically a web-based tool that will be released eventually. It's not open source. We cannot make it open source because we will find a way to make it open source. But at the moment now, if we release it as an open source, you can attack other organizations. I'm not going to sort of release a loaded gun here. This is something that, so what does it do? You write your contract in some sense once in your language that you write in smart contract. At the moment, we work at the byte level of the EVM, but we can work at different level. And then we take correctness requirement. We wrote our own specification language for correctness requirement. And this is where we write this correctness requirement. And then we develop this Certora ASL. We call it accurate static analysis. And this accurate static analysis either give you a concrete test cases that indicate the error, or it's actually proved, and in certain cases it can prove that certain things cannot happen. So it gives you both. And I've been in the space of static analysis. There have been a lot of companies in static analysis, including my own students, which had Panaya, which actually was acquired. But in static analysis, usually it's not very precise. It scales to run on huge programs, but it's not very precise. What we are doing here is opposite. We are developing this static analysis that cannot run on huge programs, but it's very precise. So it's some kind of interesting use case for this technology. We cannot run it on Microsoft Word, we admit, okay? But we can write it on smart contract. And we notice, and actually we can show you that we have this minimal false positive. So that's actually the biggest problem if you're familiar with tools like static analysis, that they give you a lot of errors, but none of them are real. For the errors we currently produce, we actually give you a test case that indicates the error and you can run it and check. The other thing that we do is we can give you guarantee. So we actually aim at the sound solution, which means that when we prove that it's correct, we guarantee. And the enable thing for scalability here, and this is a case where smart contract is a killer, the idea is that we can somehow verify each of the contracts separately. And we verify each of the contracts with respect to the requirement of other contracts. And there are some details involved, and this is, you have to see the tool, but this is the idea. So just sort of to give you a Buggy code, there are many, many Buggy codes. So this is a benign Buggy code. It's actually a very nice one. It's taken from the course of Dan Bonnet at the Stanford Blockchain. So it's a nice code because actually the students actually were given like something like to find 5 bugs. But if you look at it, actually you can find 50. And the interest, of course, this is a very toy program. It's basically, there is something that you buy a ticket and you update the price and you get the price. So I don't know, this doesn't work. But this is a very simple one. So you see, oops, somehow the video didn't work. I don't know, it's the video didn't work. I guess somehow something happened. But the idea is actually you run the code. Here it is. Let's see. I was too slow at first. What do I have? Do you have to do something? No, just a sec. Maybe it will just take. I just try to record. So basically, we work as a web-based. We tested it before, but it did work. But now it doesn't, like any demo. But it's basically identify the bug. And actually, if you look at it, the bug is actually that this contract doesn't return the change. Okay, so basically, when you buy the contract, you lose your money. So the bug here, you have to check it, and now you're moving it. So you have to check that the message value is equal to the ticket price. And now you see the code is executing. Oh, here. Now you see that we verify it. It's nicer actually when we find a bug, but the bug is not very readable at the moment. It will be. But that's actually, you see we verified the code, and it checks, in this case, it's exhaustive. It tells you that it checks all the properties on all inputs. And this is basically a web-based tool that checks the correctness of this contract. Sorry? You have a loop because it said the loop was unrolled once. No, here there was no rule, but it's actually the message information is not so nice here. Basically, at the moment, when you have program with loops, we just do this bounded unrolling. Later on, we have actually inference for invariant and other things. Thanks. So this is actually another use case of the same technology, which from an industry perspective is kind of interesting. So this is a product that we have, which is called Asset Scanner. So what is the idea? The idea, you have a smart contract, and then you have fixed set of requirements. So this is actually something that we wrote together with the customer. So we are not just, so we are checking some requirement. And it's exactly the same kind of technology, but this is much more scalable because now each of the token, you can run and check that it satisfies the requirement. For example, you can specify, you check that it satisfies the ERC20 requirement. And we had more and more rules like this. And this is a sort of a real-life data. Of course, I'm not going to show you who are the tokens. But the idea, these are real tokens. Okay, and for each of these tokens, we are checking some rules. For example, that you cannot mint a new token, that you are the owner. These rules are not necessarily bugs. You can think of them somehow as features. But the idea is, before you use a token, you may want to know if it satisfies these properties. And the red means that it violates. And for the red case, we can actually provide an input that shows the red. And the green means it actually satisfies that. So we can check all of these properties for you in many, many tokens. And that's a use case, for example, checking ERC20. And there are many, many rules that we can check. For example, you cannot mint if you are not a super user. So these are some kind of high-level property that you want to check on this contract. And we are hoping that maybe some things that we can get from the community, we can get more of these rules. If you can tell us more rules, we'll be very, very grateful to you. And we'll find a way actually to reward the people who will give us these rules, because these rules are very nice for us. So we have started this company, but we actually do get quite a very good relationship with top-rated customers. So Compound Finance is one company in this space. They are one of the few companies who have already money which is being traded. And what they do, they use our technology. And they use our technology in addition to auditing to check their correctness. And there is a difference between version 1 and version 2. In version 1, we had to write the spec, but in version 2, they are writing the spec, which is very nice. And this comes as part of their continued integration. So basically, in their continuous integration, every time they upload a new contract, they will check it with this code. And this will allow them to develop the code in a faster way, but still guarantee that it's correct, because the specification remains between version 1 and version 2. And we come with more and more rules. Another usage of this is cryptocurrency exchanges. So these are exchanges that allow you to trade other people's contracts. And they better check that the contract that they check satisfies certain rules. So that's a very nice use case of formal verification, like the SLAM. You have a third-party software that you want to check that it's correct. So you ended up, and this is, by the way, we call them code operator. And it's another interesting case of this technology, that basically the developer, they write the specification. And this specification actually is being used later on when the code is used. So that's how this is used. And you see, both cases, I think the customers are happy. So just to give you a tiny example to get the idea of the technology, this is not a real code. It's a toy ERC. And you see the invariant that we are proving? The invariant that we are proving is that you do not mint a new token. So the sum of the balance remains the same. This is a reasonable requirement, and this is a trivial contract. But even if this trivial contract, in fact, it may be violated. Because basically, as Gregory pointed out, if Alice sent the money to herself, in fact, look what happened. Before that, Alice has 50 coins and Bob has 70. and the sum is 120. And after that, Alice has 100, and Bob still has a 70. So basically, this aliasing problem, this kind of bug where you're actually sending to yourself is a big bug, and this bug is identified automatically by our technology. We did not have to do anything. We just actually run the tool, but we had to know the spec. We had to know that the invariant is the sum of the balance remains the same. And for example, once you fix the error, here you see the fix of the error is very simple. You add a solidity command that says that form is not equal to 2. Okay, so we add this command that says that form is not equal to 2. So now the technology actually can automatically prove that you have this invariant. So basically, we prove actually that in all passes, it's actually preserved that, and for all input value, the sum of the balance remains the same. So this is a proof of the technology. So what are we doing? We are trying to come with this library with the help of the community. We are trying to come with a library with specification, and basically each of the specification will be actually used. And hopefully these are specifications which are reusable, that you can write specification once, and it will be used beyond a single contract and maybe beyond a single blockchain. You notice that this specification that we are writing is not specific to Solidity or anything. They represent some things about this business that you are doing. They are not really, and we are trying to make them as high level as possible. So we are not actually trying to come up with a specification which is language dependent. So let me show you few examples of specifications. So one specification related to what we see in the next talk is the issue of DAO. We all heard about the DAO idea, that basically you have many participants which are depositing your money, and then the fifth comes and deplete the account. Okay? And how does the fifth work? There is this code that does the withdraw and it sends the money, and the fifth comes and writes this function which calls circularity, called the withdraw again. So this is the idea of how you steal the money by sort of having a recursive call to the withdraw. And we want to prevent such a bug. So the idea is that we don't want you to write the code on the left, we want you to write on the code on the right. And the code on the right is not amenable. We can actually prove mathematically at compile time that the DAO bug cannot happen. Actually, it also gives you the ability to reason actually modularly, because it tells you that everything that you prove, any invariant that you can prove it once in a while for this contract independent of other contracts. So we really prefer the one on the right. Yeah. Why is it sensitive? Oh, you are absolutely right. Thank you. Yeah. So you need to do it in a more clever way. Thanks. Yeah. But so you are absolutely right. The one on the right is not good because it's not doing the same. But thanks. Thank you. So we want to have this correctness criteria. And what is the idea? The idea, and this is something that we came in academic work together with VMware, and the idea is basically we come with some kind of criteria that is not actually dependent on the DAO. It's basically some kind of things that the database calls serializability. Think about it that we have the blue contract, and it's not executing atomically, and then there is the purple contract and the green contract and so on. For each one of them, we show statically that there exists an equivalent execution sequence in which each one of them occurs continuously. So basically, this is what the compiler proves. In fact, for this other contract, we can prove this thing. And when the user writes this kind of contract, we can actually guarantee that this kind of DAO bug will not occur. And that's what we enforce at Certora. We have a library of specs that we can write, and for example, this is called ECF. So basically, this is a property that we enforce for all contracts. And we are hoping that the community will contribute more and more of these kind of specifications. So the best specification is actually the one that we didn't write. They came from customer. So this is a very nice one that came from Jeff Hayes, who is the CTO of Compound. So what is this specification? By the way, this is a code which was carefully audited by the best auditing team, and it still has bugs, actually. It has severe bugs. And what's the specification? The specification here is something that has to do with the business. This is a business that produces money market. So the idea is that what happens is you have a loan, and the interest rate of the loan, it changes over time. And you want to make sure that it doesn't change so radically. So you see the one, I try to imitate it with a picture. So you see to illustrate it with a picture. So you see that the one at the top is actually saying that it's good, and the one at the bottom is bad. And the idea is that mathematically, it's actually specified like a property, some kind of a safety property. It says that between any 2 points of time, if the time difference is less than an hour, then the price difference is less than 10%. So this is what we feed to the tool. And interestingly, the tool identifies a rare execution sequence in which this is a bug. And that's pretty nice. The customer actually was thrilled from that. And interestingly, when the customer fixed the code, it actually shows that this cannot occur. So this is why it tells you that it's actually a very good use case of this kind of technology. If you know, of course, it's hard to write these specs, but once you write these specs, you get some kind of QA, but you get a much better QA that you usually expect because you get a very, very thorough, very exhaustive kind of QA. So maybe I give you another example, also a recent one. It's also a little bit confusing, and so the idea is every time you take a debt, you need to be able, if you pay enough, you need to be able to repay it. It seems like a reasonable requirement. Okay, I borrow money from the bank, I should be able to repay it, and it's specified in some kind of, I guess, a cleaner way to do it with temporal logic, but the idea is if the repay amount is greater than the borrowed, then the new borrow, which is indicate the borrow after the transaction, is 0. Okay? So this is something that you would imagine that the code satisfies. And it's a reasonable requirement, and I should say this is a reasonable requirement that the compound team specified. It's not us that specified, and it's a very nice property when you are doing loans based on cryptocurrency. So this code, does it satisfy that? So of course, if I ask you, the answer is no. So the idea is it doesn't satisfy that, and the problem has to do with the fact this is how money changes over time. And you see on the blue is the debt, and the green is the interest. And the interest, of course, grows over time. And the idea is that the interest is only accounted in the next transaction. That's how these things happen. So the interest is only accounted in the next transaction. So look actually what we got from the solver. We got the fact that if we repay 40 Ether, then in fact we get back 10 Ether, but we still borrow money. It's a very weird behavior. So we got a behavior that violates the specification, and we didn't expect that. We did not expect that we are not able, we paid, you see, our debts was 36 Ethers. We decided to pay 40, okay? But it's not enough, apparently. What happened is the tool actually, you see, it gave us back, refunded 10, but still we didn't actually take this loan. We still owe money. That's a very weird behavior. And actually when the customer saw that, they said, that's beautiful. We want to have this kind of tool, because how will we find this kind of things? And we tell, look, we only have to specify what you are doing. And once you specify that, and of course they fix the bug. The bug here is instead of using the borrow of the store, they have to use actually the next borrow, which is the current borrow. And in fact, this actually calculates the interest rate according to the future. So you have to calculate the interest rate as they will be, actually, because they will be billed in the future. So this is a kind of thing. So the code is tricky, but if you have a specification around, you can actually deal with it. So that's the idea. You have to write more and more of this specification. This is hard, but we will help you. So once you do that, actually we can verify. So this is, think about it like unit testing, but you have a unit testing with a tool that can check you. So how does it all work? So it's all actually work to the same thing that actually Gregorios pointed out and Michael Hus. Under the hood, we have a lot of things that we plan to do, but the simplest thing that we do is actually use constraint solver. So there are tools from Microsoft Research, from Stanford University, from SRI. They all actually have this interface of this SMT these constraints. And what happened, there is this front end that takes the program and the specification, and it generates a formula. And this formula, we call it verification condition, and it actually indicates the correctness. And in fact, if we find a satisfying assignment to this thing, it actually indicates a bug. And if we do not find a satisfying assumption, we can actually generate a proof. So that's essentially what we implemented, and all of these things that I showed you, it's actually based on this kind of idea. That we have this tool that takes the program, and usually this tool doesn't scale for large program, but for the program that we have, that's kind of enough. So here is the idea. You see, you took this ASA via constraint solving, and basically you have this, so you see this is, the program has many passes. And basically you see this is converted to a formula. The formula takes all input into account. And basically you see that the formula takes the fact that if you take the left branch, it does something. If you take the right branch, it does something. It's also checked that which pass is executed. And then you feed it to the constraint solver, and the constraint solver automatically identifies the input that leads to the violation. And that's how it goes. And of course, for this to be useful, you need the specification. You need to know what is the desired effect. So in a sense, that's what we are doing. So that's what I had to explain. I'll be happy to take more questions. And there's some information you can take on our website. We are really hoping to get collaboration here, especially in the specification and others. Yes.
So you said that the tool is not is available only through your website, but how about the specifications? Are they public? Are they available for everybody?
So the hope is yes, but the thing is that since these specifications were contributed by our customer, we have to get their permission. But yeah, the whole idea is to make this specification available and also make this specification comprehensible. Because what we are finding out that sometimes the specifications that we have are not comprehensible enough, and we're going to improve them. So yeah, we're going to make the specification, and maybe we'll find a way to make the tool open source too. But the specification definitely needs to be open. And when we ask people about how can it be the specification is open because people are worried, maybe they have some secret sources about the company, you notice that actually we are not specifying the whole behavior, we're specifying safety at the moment. So for example, we are just saying that some bad things will not happen. So we are telling the customer that the fact that they make the specification open is not necessary, and we have to convince them, of course. But it's not necessarily an advantage to their competitors. Because they are worried. They said, look, if we wrote this specification and we are compound and we have another company, so we are thinking that in this space, and that's another thing about maybe in the future, I do not know, but you are dreaming. Maybe we will dream to have we will have the blockchain of the specification. That's if you want to dream. So we will store this specification, store them perhaps on the blockchain, maybe offer later on some kind of dynamic checking. Maybe there's a bug in the SMT or bugging in our technology, which can happen, of course. So we are thinking that the specification definitely should be open and everything. And also, I should say the specification language that we came is very simple. It's actually based on VDM, which was actually produced in Denmark many years ago by Nikolai Spada and Dennis Bjorna. And we can improve it, and we want to make it more reusable so that you can reuse it across different contracts and make it more parametric. I haven't shown you, but there is actually some higher order specification. For example, you can make sure that the balance, your ERC never goes down. So there are actually some higher order specification that we support, and we probably should support more.
So when you have these conditions and then verification, as we've seen before, the EVM language at least, and Solidity, they're very, very complicated languages with delegate call and various gas exceptions and all these things. How do you deal with those? If somebody sticks, some smart contract to you, yeah.
So we handled the EVM. And basically what happened for each, so we had to do a lot of things, including for the fact that We do the same thing that Gimple does, that we take the stack machine and find bound for it. And we do all kind of simple static analysis to begin with. And then we actually model each of the EVM instruction, including, but we don't model gas, which means that if you have, so basically since we are checking safety, it means that we can have false alarm, that basically we can execute passes that the program doesn't execute, but so far we didn't have problem with it. So basically we are, and I should say in many other cases, when we don't know what to do, we do the same thing that maybe SMT tools do, we havoc. We basically say the worst case can happen. But that's another thing which is interesting at the domain. Usually when you work in software and you do havoc, you get to, so havoc, I don't know if you guys, it probably means nothing to you. But havoc means that we assume that the variable has a non-deterministic value that we don't know anything about. So that's, havoc is something in the jargon of program verification. But the idea is you assume it can, you let the SMT choose an arbitrary value and you say it's a bug. And we do have, and I should say like for example for bitwise arithmetic, because we model things in integer, we do have at the moment some few false alarms. So it is, so basically, since we come from static analysis, whenever we don't know what to do, we err on the safe side. So this means that this tool, at the moment, when you run it, you get errors, and then you have Shelly. You have the Shelly that says, are these built? And that's probably not a good idea. It will be more and more robust at the moment. But the idea is that we have actually, when we don't know what to do, we model things, or for example, another thing is pre-compiled contract. So there are some things that we don't know how to do, and we decided whenever we don't know how to do things, we do that conservatively. Because we want this tool to be available, and we don't want to be cases that we will be unsound. And even with bounded model checking, we check that the bound. So we think that in this space, soundness is crucial. In our domain, people have not used sound tool, and that's sort of another thing for us, but we want to be sound. Up to, of course, bugs, but at least intentionally, we want to be sound. So this means that when we verify a property, it holds. Occasionally, you may have some kind of false alarm. You may have some kind of error which is not real, due to some things that has to do with actually the Solidity compiler, as Grigori pointed out, and we support. The demo was not very clear, but we support all the versions of the compiler. And it's very simple. We just basically call the compiler and call the VM. It's not anything smart, but still the people like it. So basically, they actually can decide which version of the compiler they use. And we did change something a little in the compiler because we allow you to write the spec in Solidity if you want. So we have a small change to the compiler, but we are actually, the language that we took is EVM, but we can work in Tezos or other languages. But our current decision is to take EVM.
So if there's an update to Solidity or EVM, you would have to change probably the axiomatics of the semantics?
If there's update to Solidity, we do nothing. In fact, the nice thing that happened to us that we work in Solidity, and then we had customer working in Viper, and it just went just like this. Because
what if Solidity, the same code, changes semantics? I mean, it just means something different.
So the idea is that we emulate the semantic of the EVM precisely. We don't. In fact, we can catch bugs in the compiler too, and that's a lovely thing that we do. And we are in touch with, so we can catch with the thing bugs in the compiler, and that's lovely. We are at the moment modeling the EVM, and if we have enough resources, we'll model the WASM, because we believe that with the EVM, maybe Michelson, we want to model the things that people are used here. So we are not aiming at the universal language, but we are aiming at modeling, and it is true, it takes some time, so we model all the EVM instructions, and some of them at the moment are modeled only conservatively, in the sense that they actually cause non-deterministic value, and this means that if the property depends on this, the tool will say, as you say, this property failed to verify. And it will give you a counterexample, and this counterexample may not be real, because it actually has this trace, and this trace goes to this thing, and it's not the case.
So your specification language, so you have invariants, probably also have assertions, and can we think of them as just Boolean expressions over the state at that point in the program, or you also write temporal properties or more? What is the expressiveness of your specification language?
We should add temporal properties the moment we don't have temporal properties, but we do have like quantifiers, higher order things. So we do go beyond, and we have implication that you can write. So we do, basically the way we do about it, we work with the customers, and we add what they want.
Right.
So that's how we work.
But
And
now you have a dependence from the syntax of Solidity to the EVM, right? So yes, you do verification at the EVM level, but you also have to compile your specs right down to the EVM.
Exactly. Yeah. So we do that actually.
You'll have to do that for Viper as well, then.
Yeah. We have to do that, definitely. You are right, and we are talking to some ways, and we also want to add this thing to the Solidity level. That's true. And all of these things translate into assert. Yeah.
This is nice.
Okay. No. Because from the beginning, we let the customer tell us what we have to do. That's how we do.
Thank you very much.